This talk is about fundamental limits on correlated catalytic state transformation. So first of all, why? Catalysts have been used to formulate some laws for quantum thermodynamics, so involving quantum systems. So in its more general way, a thermodynamic process could involve a catalyst that is left unchanged at the end of the transformation. In this way, it was possible to identify some thermodynamic potential that characterize the transformation allowed, and catalysts have been used to enhance quantum state transformations. So in principle, they could improve quantum tasks, and the first example was already given and using in the context of quantum teleportation. So our work is what is actually possible with catalytic transformations. So first of all, I want to point out that this is a more general problem, so involving quantum resource theories. So in quantum state transformation, you could allow in its more general way for a catalyst. So what are resource theory? Each resource theory is equipped with a set of free states and free operation. A set of free states is just a subset of quantum state with some mathematical properties, and free operation maps free states in two free states. So in our work, we considered resource theory of addermality, where the free state is the Gibbs state and the free operation leaves the Gibbs state invariant, and resource theory of coherence, where diagonal states are free states, and and free operation defined accordingly. My results, first of all, what is the model? So we define epsilon correlated catalytic transformation if there exists a free operation involving our system and the catalyst. This free operation n that maps it into a state tau, and this tau is epsilon close to the ideal output rho prime tensor C. And if this holds for any epsilon, then we just drop the epsilon in the definition. We quantify the distance with this purified distance. And when we have a quantum state and the free set, we use this maximum fidelity, which is the minimum distance between the state and the set of free set, and the set of free states. And our main theorem says that if we have two states that satisfy some mathematical conditions, then for any epsilon correlated catalytic transformation, then the fidelity of the catalyst with the set of free states, the catalyst needed to transform ρ1 into ρ2 is upper bounded by this constant multiplied by epsilon. So it means that for epsilon equal to 0 in particular, the catalyst should be orthogonal to the set of free states. So this kind of distance must increase as epsilon goes to 0, and in this way it means that the catalyst should be highly resourceful as the error, infinite resourceful as the errors vanishes, basically. So we in our specific resource theories, for addermality, we quantify the resource of the catalyst using the non-equilibrium free energy. So we get this divergence of this free energy as epsilon goes to 0. For resource theory of coherence, we have the same, but we use the relative entropy of coherence. Comments of conclusion. So we first focus on the problem of catalyst preparations, and our results apply to any correlated catalytic transformation, and in principle applicable to any resource theories. And there is a trade-off between the error achievable. We realize how this trade-offs between the error achievable and the resource needed to prepare the catalyst, and this means that this kind of settings everything must be formulated in this asymptotic way, because in general we wouldn't be able to achieve epsilon equal to 0. And we establish also in our work that a recently proposed procedure is optimal, and something about embezzling, which means that this kind of embezzling would involve highly resourceful catalyst preparations, and our limits will have to be taken into account for any future theoretical consideration and practical considerations. Thanks.